Hello back. I I'm gonna continue with chapter 6. I hope you're doing well. So let's get started on graphing cosecant and secant functions. So that's where we stopped last time, and I talked about tangent and cotangent functions, and I have to admit that probably secant and cosecant are the easiest ones to graph, even though they may not look like, easy graphs. But if you think about it, cosecant is 1 over sine. So the way we can do this is by graphing sine and literally take the reciprocal of the graph. So basically, wherever this graph, the sine is increasing, the other one, the reciprocal, is decreasing. And wherever the sine is decreasing, reciprocal is increasing. When you take the reciprocal of a number, that's the relationship they have, right? Because reciprocal of a number is 1 over a number. So if this increases, this one decreases, right? And of course, if this number is 1, they're the same. So as you see over here in this rectangle, we're going to limit ourselves to one cycle of sine, which it's right here, right? So that's one cycle of sine. And at this point where sine is 1 or negative 1, the reciprocal would be the same, right? So they share that point. Otherwise, if one of them increases, the other one decreases. So they share those points, and that's it. So what is the domain of cosecant? Well, the cosecant will not be defined when the denominator is 0. And we know when sine is 0 in the unit circle, we know when sine is 0 over here and over here. And of course, in the graph of sine, whenever it crosses the midline, at that point, at this point, at this point, at this point, we have vertical asymptotes. So in one period 2 pi of sine, there are 3 vertical asymptotes we have to graph. See, where sine crosses its own midline, we're going to have to graph the vertical asymptotes. And then it's very easy to graph cosecant. All you have to do is, from this point, this goes to infinity this way. And notice that it looks like we're just flipping this graph. And this is like an upside down U, and this is, upside up kind of U, right? And the other one too, over here is negative 1, so it goes to negative infinity this way. This goes to negative infinity this way. So this right here is one cycle of cosecant. And the other cycles are the same things. You just graph the cycle of sine, and then on the top of the hills you put valleys, and on the below the valleys you put hills, right? And that's it. So the domain of cosecant is going to be all real numbers except for any x that is in the form of k pi, a multiple of pi. So that's the domain. So all real numbers except these numbers. Now what about the range? Well, if you look over here, let me clean it up here. So the range up to 1, right? 1 is included here, and negative 1 is included, right? Negative 1 is included. But then all the numbers below negative 1 and all the numbers above 1. So the range is all the numbers below -1, including -1, union all the numbers to the right of 1, including 1. So we put brackets here. So this is the range, and the domain would be all real numbers except a k pi. Now, there is a way to write the domain in this form too, but it requires more mathematical notations, and we don't want to do that because we don't have just one interval, we have a union of infinite number of intervals if we want to write the domain this way, right? So what do we have? We have all these, all these intervals, 1, 2, 3, 4, right? So we have to write the union of all infinite number of intervals. We can do that with a symbol in mathematics. There's a union like that, and it could be a set. But we're not going to do that because it's not really necessary. But in more advanced mathematical symbolic language, you see stuff like that. Okay, so for now we don't need it. We just say domain is all real numbers except those. Or you can say x not equal to k pi. All right, so that's one cycle of cosecant. So really, we don't have to create a table. We could create a table, but why? I mean, it's so easy to graph. So obviously, when sine is 1/2, right, cosecant is going to be 2. See that? So we can do that. We can take a bunch of points, right, like we did before, and then see what we get. But we don't have to. So that's the way we graph cosecant. Now, secant is the same kind of situation, except secant is 1 over cosine. So what we do, we graph one cycle of cosine, as you see over here. One cycle in what? One cycle in the domain of 2 pi, right? Remember, cosine looks like this, right? In 2 pi. So we put a line in the middle here. So there is a half a hill, right? And a half a hill here, and there is a valley in the middle. So if you graph this in 2 pi, then of course we don't want cosine to be 0 because then is undefined. Well, you can go to unit circle and realize that cosine is 0 here and here, and those are odd multiples of pi over 2. And we talked about this already. Odd multiples of pi over 2. So whenever we have odd multiples of pi over 2, so 1 pi over 2 right here. So basically at the points where cosine crosses its own midline, we have what? Vertical asymptote. So for secant, we have in one period, we have 2 vertical asymptotes, right? So it stops right here. So we graph this half kind of valley for this half hill, right? For this half hill, we graph a half valley, and then for this complete valley, we graph a complete hill here, right? And then for this half hill, we graph this half valley, right? So one cycle of secant looks like this. And the period, of course, is the same as cosine. And I think we forgot to mention, period of cosecant is also 2 pi. So period of secant is 2 pi, one period of it. And that's how we graph it. All right, so the domain of secant is all real numbers except these. And the range is the same as cosecant. You go from negative infinity to negative 1 and from 1 to negative infinity. Again, we could graph this point by point, but there is no reason for that, right? For example, cosine of 60 degrees, we know is 1/2 right here. So we know secant of it is 2, right? And so forth. All right, so one cycle of secant is graphed this way. Now, of course, we have to transform secant and cosecant just like we transformed tangent and cotangent, because we might be given, equations like this: 3 cosecant 3x minus 1 plus, 2, something like that. Well, how do we graph this? Well, it turns out that if you graph, so if you want to graph cosecant, you graph y equals to 3 sine, exactly the same thing. Just like we did here, we graphed cosine first and then graph that. We can graph 3 sine 3x minus 1 plus 2, which we know how to do, right? Once we graph a cycle of that graph, which is 3 sine 3x minus 1 plus 2. Let's say we graph that. And then what we do, we're going to graph it in a dotted form. So we graph that, which is going to be a sine, a dotted line, right? And then where it crosses its own midline, we are going to put what? Vertical asymptote, right, where it crosses its own midline, right? There. And then, here you go. So that would be the cosecant that we want, right? Now, this rectangle, of course, is the rectangle that this fits in, right? This fits in this graph, and we know how to do that. We just transform the points, right? And we did that before for sine and cosine, and tangent and cotangent. So for secant and cosecant actually is easier, because you go back to sine and cosine, and then just flip the graph. So that's how we're going to do it. So here is an example of f of x equals to a cosecant bx minus c plus d. Again, a capital A for secant and cosecant is not amplitude anymore, because notice that cosecant, it goes to infinity, right? So amplitude doesn't make sense. And again, period is 2 pi over absolute value of b, because the period of secant and cosecant is 2 pi. And then c over b is still the phase shift, and d is the vertical shift. So everything else is the same. So to graph this, we first graph this. Then what? When we graph this, as I said, we're going to have a sine in a rectangle like this. One period of sine, right? Kind of like that. And then where this crosses its own midline, we are going to put what? Vertical asymptotes. We have vertical asymptotes at where it crosses its own what? Its own midline. And then we graph cosecant, like that, right? So first we graph this sine in a rectangle like that, then we can graph this easily. Now, one common mistake is that students think that this function is a reciprocal of this function. That's not true. It's not that this whole function is a reciprocal of this whole function. That's not the case. So this is not equal to 1 over, a sine bx minus c plus d. That's not true. Okay? So that's not true. What is true is that cosecant of b minus c, bx minus c, is 1 over sine of bx minus c. That's true. And then, since these two are the same, then if you put an a here and add d here, you could do the same thing here. You could put an a here and add d, right? So these are the same. So don't make that common mistake. All right, so it's time to actually do an example, right? So remember, the vertical asymptotes for cosecant is at the points in the rectangle where the sine crosses its own midline. Now this midline may not be the x-axis, okay? Because this rectangle may be up here. Let's say you get a rectangle up here, right? Still, what you do, the vertical asymptotes would be at these points, right? So you graph them. Where it crosses its own what? Its own midline. All right, so now that we got all of these under control, we are going to actually graph one. So secant, we do the same thing. If you want to graph secant, we graph cosine, right? So we're going to graph cosine, a cosine bx minus c plus d, just like I just did for sine. So you're going to end up with a cosine rectangle. Then you're going to get something like this, right? Of course, you do a dotted line. And where you see it crosses its own midline, you're going to put vertical asymptote. And then you do a half valley here and a half valley there and a complete hill over here, like that. That's how we graph this. Again, it's not true that this whole thing is a reciprocal of this whole thing. That's not true. Only this part of it is the reciprocal of this part. All right? All right, so let's do an example. So here is the graph we want to graph. So what do? We are going to graph 2 sine pi over 2x plus 1, right? And we know how to do this. We transform the 5 numbers from sine function, right? So this is the graph of just sine x. We are going to take those, transform it into the graph of what? The graph of this. Once we have the rectangle, which is the graph of that, then we are going to graph what? 2 cosecant pi over 2x plus 1. All right, so we're going to take those numbers and transform them. These are the points, right, that we have to transform according to these transformations here. What are the transformations again? If you have a point, let's say a and g of a on, let's say g of x equals to sine x, then what happens to it? Well, the a part, if you put pi over 2x equals to a and solve for x is going to be a times 2 over pi. So it's basically 2a over pi. So I know that this x goes to 2a divided by pi. So all the x coordinates, I can easily transform them into what? Using what? Using this formula. So for example, first one would be 2 times 0 over pi is 0. 2 times pi over 2 is pi over pi is 1. 2 times pi over 2, right? 2 times pi over pi is 2. 2 times pi over 2 is pi over pi is 1, so forth. I'm going to show you in a second the work. But the x coordinates transform this way, And the y coordinate, as we discussed before, you have to think of this as g of a. So what happens to g of a? You multiply it by 2 and add 1. So multiply it by 2 and add 1. So all of these points now are going to get transferred using what? Using that. So let's do that. So here you go. We're going to get 0, 0, transform it. We get 0, 1. Right? We're going to get pi over 2 and 1, which is this one right there. So this one is that one. This one is that one. This one is that one. It gets transferred to 2, 2, 1. And this one is, where is that one? Is right here. And this one is right here. So that's how the points get transferred, right? So this first one gets transferred to that one. Second one gets transferred to 1, 3. That one gets transferred to 2, 1. This one gets transferred to 3, negative 1. And the last one transfers to 4, 1. Oops. Is here actually, not there. 4, 1. Okay? So those 5 points, we know where they are. In a second, I'm going to graph them. But we also need to transform the vertical asymptotes. There are 3 of them. Right? This one is x equals to 0. Right? Where does that go? So we know what happens to x. This is what happens to x. So we get 2 times 0 over pi. So that one doesn't go anywhere. It stays at x equal to 0. Now what about this one, which is x equals to pi over 2? Well, that one, x equals to pi, I mean, that one goes to x equals to 2. So we got x equals to 0, x equals to 2. And what about this third one right there? Where does that go? Well, that one goes to x equals to 4. So we're going to get these numbers, the 5 new numbers, new points, and then these 3 vertical asymptotes, and we are going to graph them right here. See? I'm going to graph all of them. Remember the first one was 0, 1, and then 1, 1, 3, and then this one was what? Was 2, 1, and this one is 3, negative 1, right? And that one is 4, 1, right? So those are the 5 points. Now, the vertical asymptotes is x equal to 0 here, right? This one is x equal to 2, and this one is x equals to 4, right? So we graph those. We got those points, so we know where the rectangle is, right? The rectangle is about right there. That's the rectangle for what? For that sine function, right? And here is the midline of it. And notice that where it crosses the midline, we have what? We have vertical asymptote. See? Of course, we transform them, but we could have just, noticed that over here, it crosses its own midline at those points, so those are the vertical asymptotes. Okay? So this is really easy to do by hand, but you have to do a bunch of them, right, to understand the structure. So this graph, this dotted graph, under this transformation turned into this blue graph. So then that green one automatically transforms into that red one. So instead of working directly with cosecant, we work with its reciprocal, sine. Okay? Now, secant is the same kind of setup, so it's not very different. So I'm not going to do a secant, but I'm going to find the domain and range of a cosecant function. So what if you're given this function, and you're asked not to graph it, but just to find the domain and range of this. Now we know the domain and range of cosecant x, right? So we know the domain of cosecant x is 1 over sine, and sine cannot be 0. So the domain is all real numbers except that. And then the range is basically all y numbers, all real numbers y, except for what? Numbers between -1 and 1, right? Remember, we said the domain is from the range is from negative infinity to -1, union 1 to infinity. So if we put this on the number line, not on x number line, on y number line, like this, here is 1 and here is -1. We do one, -1 and 1, and all the numbers on the top and all the numbers at the bottom. So what is left that we don't want? So you can say all real numbers except when y is between -1 and 1, right? So two ways to write the domain. Now it's easier for us here to take this and transform it so we get the restriction transformed, right? Instead of working with 2 intervals, we can work with 1. All right, so what we do, we're going to take this, and we're going to take this restriction here, and we're going to transform the restrictions. Is easier. What transformation? Well, we know the transformation. This is the same function we just graphed. So these are the transformations. This happens to x values, and this happens to the y values. So we're going to take the old x values, which are the restrictions, right? And then apply this to them, right? So the new x is going to be 2 times the old x divided by pi, and then new y is going to be 2 times the old y plus 1, right? So we're going to take these instructions to transform these two restrictions. In a second we want to do it. Okay, so here you go. So on the top you see what we have, instructions to transform the restrictions. So restriction for x values is that. So this is these are the old x's, right? So the new x values would be restrictions would be 2 times, right? 2 times the old x divided by pi. So 2 times k pi divided by pi is 2k. So restrictions for the domain would be all real numbers except for 2k, which means what? K is an integer. That means except for all the integers. So we have to get rid of all the integers. Integers are not in the domain. That means this thing has vertical asymptote at every integer, as you see over here in the graph. You see every integer, even integer, not every integer, every even integer, because it's 2 times k. So you see 0, 2, 4. So the vertical asymptotes are at even integers. So the domain of this new function, which is that one, the one that here, this one. Now remember, we didn't have to graph to do this. So the domain of this is all real numbers except for what? Except when x equals to that for k in an integer. All right, so that's the domain. Now what about restriction for y? Well, we know the restriction for y is y cannot be between -1 and 1. So these are the old y's, right? So we say, okay, the new one would be 2 times the old y plus 1. Here's the old y. I have to put it there, right? And on the right, we have this y, so we put it there. So the new y is going to be between what? The new y would be 2 times -1 plus 1, between that, and 2 times 1 plus 1. So the new y is between -1 and 3. That means we want all numbers before, we want, these are restrictions, right? We want all numbers on the number line all the way to -1, including -1, And so all of those, let me put the smallest one first. Let me put it here. So we want -1 and all the numbers before it. And then we need 3 and all the numbers after it. Why? Because these are the restrictions here. Right? This right here is the restriction. Y cannot be those numbers. I should have put it on a vertical line because it's Y actually. Maybe this way. So this is 3 and this is -1. So we want all of these numbers and we want all of those numbers. And that right here is the restriction. Right? Alright, so that's how we find the domain and range of cosecant and secant. In fact, you could do that for any of them, right? If somebody asks you, let's say this is sine here, right? You want to find the domain and range of it? Or you do the same thing. Take the domain and range of the sine and transform it. But since domain and range of sine is all real numbers, right? Domain of sine is all real numbers. Domain is always all real numbers. But the range of sine can change. So we take the range of sine, -1 to 1. And if this is a sine pi over 2x plus 1, then we apply what? We apply that to it. Right? To find a new range. Alright, so you can use this method for any of the 6 trigonometric functions. Alright, so in the next video I'm going to do, that's the last one for chapter 6, and I'm going to talk about inverse trigonometric functions. So suppose you have a function, sine x, and this is the function machine, so you input x and you get output sine x. What if you change your mind? We need a machine that inputs sine x and then x comes out. And that machine is called the inverse of sine. And the notation for it is, of course, that. And we're going to talk about that in the next video. Okay? So I'm going to come back here and say bye to you, and I hope you're doing well and take care of yourself and others, okay?